Okay, so like we said, PCA is used to reduce the dimensionality, which means that if we add 30 plus features, it can be reduced to even less than 10 features, less than 10 important features. And it is these 10 important features that we now use to base our to actually do the regression of the task that we may want to perform. Now, in this reading, we are going to look at in this class, we are going to look at PCA in action, the practical approach to PCA, because we had looked at the theoretical approach to PCA. And therefore, the first step is we will require requirements of TXT with all the requirements like pandas, numpy, scikit-learn, seaborn, matplot, and joblib. Because you know what each and every one of them does, and this one we shall cover in depthly tomorrow, the joblib one. So we import what will be required for our task. I just want to focus on model selection where we import trend split and grid search CV for parameter tuning and trend split for splitting the dataset. In remember, because we are working with logistic regression, we most probably want to classify then evaluate. That is a supervised learning technique. Then we also want to import standard scalar. PCA really loves scale data, and you saw we first of all scaled our data. Then we implement PCA, then logistic regression. One thing that's going to stand out is the fact that we are also going to form a pipeline. A pipeline in a machine learning pipeline is actually uh, not like a data pipeline that we built during data engineering, but in this case, it incorporates processes. It's basically a process through which machine learning tasks are done from point A to point D when we now get our results. Then we also import metrics like accuracy score, precision score, recall score, all the way up to rock curve. Of interest will be accuracy score. And of course, I talked about the pipeline, which is also implemented from scikit-learn. So a pipeline is a process. So with the pipeline, you can just onboard processes. For example, with the pipeline, I can onboard grid search CV, the onboard standard scalar, PCA, logistic regression, so that all this happens in at a go in one run. So after that, we then set up logging. Logging, I told you, it helps us actually identify errors, and not just errors, with the basic information of logs, so as to debug errors accordingly when our machine learning goes off, especially in production. We are able to see the logs, and we are able to see where the problem is. Then the random seed for reproducibility, which allows you to do random sampling. Then we now work with our telecom chan dataset. It is this telecom chan dataset, if we can open it for wherever it is. So as you can see, we have the customer ID, gender, senior citizen, partner dependency, all the way up to chan. So all these are features. We want PCA to help us. First of all, we'll do one hot encoding. Then after doing one hot encoding, we are going to now have a very broad dataset. Then we will want PCA to help us actually by now trickling down to the least, like to the best components that we may want to use. For example, it might trickle down to online backup, yes, dependence, no, something like that. So at the end of the day, we only use what is of importance, and that's the main beauty of PCA. Then we pre-process our data. To pre-process the data, it basically means that we make data readily available for analysis and conforms with our requirements. One of the things that we must do is to ensure that if we have any data that should be numeric, then it should be enforced to be numeric, and that is actually what Pandas is doing here with the total charges. And the total charges, we also fill null values. I told you machine learning is always very, very subsequent to null values. So we ensure that we fill all those null values using fill NA, and we use the median to fill for the null values. Then we drop the customer ID because we do not need it. It is just for primary key purposes, and in this case, we are not merging any data set, so we do not need it. Then we select the categorical features. We select the categorical features that we are going to work with. And as you can see, Pandas has a very powerful way to select the categorical features. One of them is called df.select data types. This one here, D types. Then include objects. So as you can see, this one most probably can be a list. So if you had more than D types that you wanted to include, then you could have just continued with the list here. But since we're just including one, there is no problem. Then pandas allow you to change it to a list. And from the categorical features, we remove chan. Then we get dummies for all the categorical features. This is actually one hot encoding. We did not get dummies. We now get dummies for one perform the one hot encoding, which I can just say here. This is one hot encoding. Then df chan, we map df chan because I told you that we probably want to work with numerical data. So the map function in Python is a very powerful tool that transforms values from one data type to another. A good example is yes can be now transformed to one and no can be transformed to zero. It's actually used for label encoding. So this is called label encoding. So once you have all these at your fingertips, there is nothing that can actually scare you with processing data. Usually in big techs, when you have been called to the interview for big data, what they do, they always ensure that you can clean the data well and also ensure that you can use pandas at it. So that was just a reminder. Hakuna kitu new hapo. So let's proceed. I told you that these things actually what the only thing that can ly. I don't know why, but let's hope it that my nini has refused to work kabisa. Yeah, yeah. So I had to remove it and install a new one, but still no. Working with Windows, jamani. Then we now split the data set. This is self-explanatory. Of course, you have X, you have Y. Then you split it using X train, X test, Y train, Y test. Train test split X, Y, test size. Random seed is 42. Then uh, stratify is Y. This is optional. I don't know what it is. I can't lie, but you can go. We can go to the documentation and see. So stratify, you go directly. If not none, data is split in a stratified fashion using this as the class labels. Read more in the user guide. Because the stratify I know is what is called stratified sampling, which we looked at during my statistics for data science. And we said for stratified sampling, data is split into groups called strata. So maybe this is what they also want, that due is stratified k-fold is a variation of k-fold which returns 35 folds. Each set contains approximately the same percentage samples. Okay, so it's just sampling format. So in this case, we are saying that the sampling format that should be done is actually using Y. Then we can now log the info that the data, the channel split has been split, the length of X string, for training and the length of X set for testing. Once this has been prepared well, we can now proceed to apply PCA. I told you that PCA works best with scaled data. So first of all, you must scale the data. Then after scaling the data, you fit scalar.fit transform on X, while scalar.transform on X test. Look at what has happened there. Scalar.fit transform on X and transform on X test. We can go, so just transform on X test and fit transform on X train. So if you come back to our documentation and search for standard scalar, yeah, something like that. That's a standard scaling. So scalar.transform, fit transform, fit to data, then transform it. That is why fit transform is done. So it will fit transformer to X and Y with optional parameters, fit parameters, and returns a transform value by version of X. Whereas scalar.transform just transforms it the data set. Transforming in this case is actually what performs standardization by centering and scaling. So this is what we mean by transforming. So the difference between fit transform is that the X1 will fit the data to will fit the scalar to the data because it's the one that you're using for training. Then transforming it, meaning scaling it. While for test, we are just scaling it without fitting it to the data because the data set is just used for evaluation. Then we proceed to now defining PCA. Then PCA, we put it on X-train scale. Then explain variance ratio. We look at cumulative sum of PCA has a certain method called explain variance ratio. Explain variance ratio is the percentage through which the X variables will explain the Y variable. Yes, like the regression up there. Then the number of components should be, we should take from, we should use NumPy to look at the explained variance ratio which are greater than 0.95%. That is actually the number of components. Then we add that to 1. For example, if we had variance, what we're trying to say, the principal components which has a variance greater than 95%. And if they are there, we can add 1 for allowance purposes. Yeah. So then you can see the variances. So let's try and run this. I don't know why it just refused. I wish it could work well. I hope it will run in your case because mine has a problem with, I don't, that's why I don't like Windows. Once we'd have done that, now we can apply PCA with selected components. Look at what we've done. We select the components which has the variance ratio of greater than 95%. Then after that, we do what? We apply PCA with the selected components only. So PCA is equals to PCA, and components is equals to number of components selected. Then we do extend PCA, PCA.fit transform with extend scale, then extend PCA is PCA.transform X scale. Then after that, we visualize the explained variance. Visualize the explained variance. Hey, this thing ought to function. Oh, okay, it's running. So the problem is data set. You can tell that. But ah, this was self-explanatory. I didn't put R here. Good. So we can continue. So out of the 30 plus components, 17 components now have an explained variance of 95%. 95%. So the number of, yeah, so you see we have 30, then the cumulative explained variance. So at 95%, we have 17. At about 100%, we have nini. So we remember greater than 95 and above. So we have 17 items. So that's basically what we are looking at. Now we are visualizing that the PLT dot plot range between 1 to the length of explained variance plus 1. Why are we putting plus 1 here? Because I told you that when you use Python range, it will start from 1, then a length of explained variance ratio, which is 17. So when you take the range of 1 to 17, it's going to start from 1 to 16. Python does not include the last one. So for you to capture the 17, you must put plus 1. Then you do it against the explained variance ratio. The explained variance ratio is actually now the y variable. Then you mark with 0. So if you with X, you know what it's going to do. Then the number of then the the average line is actually this one. You see this red one, and I think it has been given a color. Is the number of components that we were looking for here. If you look at the number of components that we were interested in here, of which we found out to be 17. Yeah, then we are saying that the color should be red, R stand for red. Then the line style should be that one dotted. Then we have the label. You to label is just to name it. The label components 95% variance. What has been done here. This is what we encountered during data analysis, data visualization using Python PLT to be precise. Others are just self-explanatory, like title, mini, legend, legend. We also have save the figure, which is going to save it, especially if you are to share it with the stakeholders. Then we store the figure, which is now here. So the only courses that could have caused problems in explanations are these two. Then once we've now known that 17 components, remember when we were fitting logistic regression back then, we were doing it on all the components. But now PCA has helped us uncover the principal components. And you can see how the large data set was, which had 30 plus features. We've now removed 13. We are remaining with 17. So it is this 17, it is from this 17 that we are now going to ensure that we fit the logistic regression. So we build the logistic regression and we implement it using a pipeline. So in this pipeline, which I told is a process through which things happen, uh, we start. That is very right, and that's what we call the important features of the principal components. No, that's not applicable here in the PCA. Here in the PCA, what we've done actually, remember the theoretical approach to PCA back then. So in the PCA, what we've done, we've scaled the data set. Then we've started. Let me just pull up to be precise. Don't confuse logistic regression, which is even not a regression per se, with linear regression. Logistic regression is used for classification. So PCA is like a pre-processing step here, which is just used to reduce the dimensionality. I want you to see what we've done with the PCA. This is what we've done with the PCA here. This step here. So we have the feature and we have x1 feature. In this case, x1, x2 will assume the following. If we're the telecom data set, x1, x2 will be gender, senior citizen, partner, all the way up to the chan. Then after doing that, we now say example one, example two, example three. Then the first principal component, the second principal component. I told you these are gotten depending on uh, the number of even vectors. So it is these principal components that we have calculated. We've not calculated t-test. So all this theory that we learned before in theoretical approach to PCA has been implemented by this code here. Yeah. Okay. We now put them into a pipeline. The pipeline. The first item in the pipeline is to scale the data. We call it a scaler. The second one in the pipeline. Oh, this pipeline has this format, by the way. It is a tuple which can now carry a list of items. Then the list itself also has a tuple of items again. Yeah, so PCA, then logistic regression. We now also implement it using a pipeline. This pipeline, this is how it is interpreted. That before you do PCA, you must do scaling. Then the logistic regression must come last. We might also tune hyperparameters. One of the hyperparameters for logistic regression is what we call the C regularization. This C is basically the C that we talked about in a support vector machine. So this C helps us regulate the. So I want us to go to a parameter tuning for logistic regression so that you can see how it is done using C. Then we also have another one called solver, and the different types of solver include the library linear and LBFGS, which you're going to see what it stands for. So when we now come back here, we can look at the logistic regression. Just type logistic regression. So we have the following parameters. We have the penalty, the dual, the toll, the fit intercept, the scaling, the random state, all the way up to the L1 ratio. So this logistic regression this class implements regularized logistic regression using the linear library, Newton, CG, SAG, Saga, and all those solvers. Note that regularization is applied by default if you do not specify. Now, when we come back here, we are specifying two regularization techniques. One is the solver, which is linear, either the two of them, and another one is a C. So let's focus on what C does. Did I pass it somewhere? There's so many. So for example, if penalty is actually specify the norm of the penalty. None, no penalty is added. L2 adds L2 penalty tower is the default choice. So all these, then we have elastic net, both L2 and L1 penalty terms are added. Then you might want to ask yourself, what are these L2? These are just basically regularization techniques. Then we have the dual. Are you there? Hey. Sorry, someone interfered with my internet. Can you hear me? And I hope you can also see my screen, or not yet. Can you see it now? Eh, eh, This one now in my end. So can you now see it? Okay. So the C that you are talking about is the inverse of regularization strength and must be a positive float. Like in support vector machine, I just said that smaller value specifies stronger. So in support vector machine, what did we say about the C? But the way it is the C that has been borrowed from the support vector machine. Yes, I'm using the phone one. I don't know. The one in the house has just stopped. And yeah, just wait for it the other day. So I don't know what the problem is. Just a minute. Let me try and change the internet. It should now work. Okay, confirm if it's now better. So we were talking about the here. So let's look at the C in support vector machine. See here, we say that it is a margin maximization and misclassification fines are balanced by regularization parameter C in SVM. The penalty for going over the margin or misclassifying data items is decided by it. So a stricter penalty is imposed with a greater value of C, which results in a smaller margin and perhaps fewer misclassifications. So C is basically used to ensure that misclassifications are not happening. Like in our case, we are going to ensure that items are not misclassified. New data items arriving are not misclassified. In support vector machine, it should be large enough so that at least because of the distance here, so that the distance is minimized. Remember, support vector machine works with the distance to the hyperplane. But when we now come back to logistic regression, smaller value specifies stronger regularization. That's now the difference there. Then we also have a solver. The solver is an algorithm to use in the optimization problem. Default is the LBFGS solver. To choose a solver, you might want to consider the following aspects. For small data sets, library linear is a good choice, whereas SAG and Saga are faster for large ones. For multi-class problems, all solvers expect library linear minimize the full multinomial. Then, library linear can only handle binary classifications by default. Binary classification by default. So when you come back to your data set, what types of classification do we have? Binary classification. That's why it's been used. So it has been used to take care of the binary process. Then LBVFGS is used because it is by default the one that is mostly used for large, relatively smaller to large to medium data sets. So that is what the hyperparameter tuning entails. Then the grid search CV is now going to be implemented using the pipeline, then the parameter grid, then the CV, then the scoring should be accuracy. Then the number of jobs, as we saw the other time, is -1 by default. Now, grid search CV is telling us that we implement the pipeline and look at the pipeline as a scalar PCA and logistic regression. Then the parameter grid. So you can imagine how powerful this grid search CV is going to be. So it's going to implement this scalar PCA LR on the C of 0.01 and lib linear. C of 0.0.1 lib linear. C of Ivo until you exhaust C. Then you start again with lib linear with every value of C. So it's going to be very, very much complex. That's when you fit the grid search, you now fit the grid search CV on X train and Y train. Then the best model is the best estimator from the grid search CV. The best estimator, this one is a predefined method that we get from the grid search CV model that you have defined here. So you also get it from the scikit-learn package. It is actually going to give you the best estimator after you've performed the permutations or the grid search CV that you did up here. Then you use the best model now to predict for our values. And accuracy score is now 0.7913. Logistic regression for classifying items, let's see the accuracy score of the previously. That is customer Chan and sample learning. Hapa tulikuwa na time sana. Eh, Hey, we really had a lot of time here. We did all this. So look at that. From 0.73 all the way up to 0.79, which actually for with this you can now deploy your model mm, like with higher confidence. Yeah, because it's closer to 80%. So that is why PCA is important because it has helped us choose the best the best features. But without the PCA, maybe the reason why it was 0.73 is because we had actually developed and implemented our model with the wrong uh, with the wrong features. The confusion matrix, self-explanatory. I'm not going to dwell on that. The rock ICU curve, we've been talking about this. I highly encourage you to go and do more research on this. Then I wanted to us now to classify the new features. We have the input. We define a function. This is also another idea which is always tested when you are applying for data science. You write a function that will classify new features from a simple logistic regression. Alafu you start looking like features trained on. No. It is very easy. First of all, you just define, classify new input, then put then the arguments. In those arguments, never miss to mention the data. The input data, then the model. Scalar is optional, but input data, the model, and also the columns which you are going to use. So we use a try except handler in Python. We try the input df to be pd.data frame input data, then input df, and of course you know that the input data we are now going to supply down here. So then this means that any input data that you're going to supply will be changed by into data frame using this function. Then again, the input df, we are also going to get dummies on the input df, then columns for a column in input df.columns if the column exists in columns. That is always for a senior a senior engineer who will always write codes like this. This is a for loop with a condition inside it. So just to say that we have input df dot columns. Of course, input df because the data frame it will have columns. So for columns in columns, if there exists a column, then we just name it a column. So one line of code has actually is calculated the for loop and also a conditional statement there. But then this is always tested. You see what is inside here. It is always tested exactly as it is, and you will find a company giving you this as the first step for technical review. Then they stop it at that point. They don't continue. Then yeah, just like that. Then input df is equals to input df dot the index, the columns, then prediction. You predict using the input df, then probability, then but if you cannot classify, you now throw an error. Now, example usage, we supply the sample input. The input df will be the sample input. When we classify the new input, look at where the input df was. If you reorganize things, it will not work. So it must be the way it is. Input df, then the best model, then the scalar, then the columns. And after that, prediction churn, this guy will not churn out. Probability of churn will be lower at 0.3430. Yes. Once we've tested that it's working, and remember this is at 79.13% confidence. So then we now save the model for deployment, which we'll now deploy tomorrow. You've now seen the practical aspect of PCA. Yeah. Yes. Powerful feature. Powerful feature engineering technique. Thank you for that. Is a very powerful question. PCA, that is it. It is used to identify the most important features, but use it with caution in recommendation engines, because in recommendation engines, all features are important. In that, you saw what we were doing in the item set. In the item set, we say that someone can just come from nowhere and purchase something that he was not purchasing before. He had not purchased before, or he had never purchased before. So when you remove this feature as not important feature, yet we will need it for item set, use it with caution. So to answer you, yes, but when it comes to recommendation engines, you use it with caution. Yeah. Monte Carlo research. But before we do this, let us look at the theoretical approach. So one thing I missed, there is something that after rollout and simulation, we were supposed to be deleting. I was not deleting that, and that's where the problem was. So the formula, upper confidence bound of 1 is equals to V, that is Vi, plus 2 into root of ln all over Ni. That is the, the, the number of simulations that have been done. Now, when we are beginning, we have the total point cumulated to be 0, and the number of actions taken is also 0. So we are beginning at this point. Then we are taking some actions A1 and another action A2 here. So this one leads us to t is equals to 0 and n is equals to also 0. But the same thing here, t is equals to 0 and n is also equals to 0. Then we roll out. So when we roll out, we randomly assign a value of v. When we randomly assign the value of v, it is random. So let's say we've assigned it to be 20. Probably this one will be assigned. We will now come back and delete this. The rollout, the rollout done. Then after deleting it, we are now going to put 20 to be here, 20 here, and now the number of actions that have been taken is now 1. Are we together? Then this one is also back propagated back into the child node, the root node. So probably the number of actions, and it is highly recommended that you now put this as capital N because it will keep on increasing, is 1, while this one is 20. Then we use the upper class bound to calculate. So it's going to be 20. Remember, it was always T all over Ni. So it's going to be 20 all over 1 plus 2 into the root of ln of 1 all over 1. This one, when you calculate, I don't know, where is that? Our old calculator. ln of 1 nakwanga 1 ama ngapi? You can do it on your end. Is it 16 point something or 11.67 if I'm not wrong? Yeah. You copy. Okay. What we know, this is some value. Let's work with 16, not to waste time. But this is going to be infinity. So again, when it is infinity, we roll out from the infinity part. Yes. So it is a larger UCBI. Since this infinity we rolled out, we also randomly assign a value of v. It is random. So the machine will always send a random value. So let's work with a smaller or a larger v depending on your preference. But let me now work with a smaller v like 14. So this 14, we now calculate the upper class bound of 14. 14 all over 1. And remember, if we assign 14, it basically means that this one is coming to be this, and this is 14. And now this is going to be 2. Alafu huku juu ni plus 14, which is equal to 34. Yes. Then this plus 2 into root of ln of 1 all over ln of now 2 all over n. Y hapo ni 1. Now after doing that, let's say you find it to be 11.67. So we delete this again. We delete this. And we note that here to be 11.67. If you compare 16 and 11.67, 16 is larger. So we also come back here. So that is the step I missed. I don't know, the reason why I love Monte Carlo is because maybe it has lots of maths. I love something that is purely theory, to be honest. Yeah, you see, machine learning at the root of, like at the core of machine learning is just maths. There's nothing else. So this is 16.67. So we put another action here, A3, A4. In this A3, A4, it gives back to a certain child. Remember, this is state 1. So this one becomes state 2, state 3. So this is going to be state 4, state 5. So with this, so are you now seeing what the sarsa means? Yeah, so this is actually what we are doing here. Now with this again, we just say then that t initially is 0. And it's also because we have not taken any action. So because these are equal, it is we can take either. But let's go with the numerical. S4 is so we start with S4. Then we simulate here. If you can take v is equals to 0, then it basically means t will be 0, but the number of action will increase to 1. Then when we back propagate here, the number of action will be 2, and here it will be 3. Then now, in this case, it's going to be 0 all over 1 plus 2 ln of 1 all over 3 root of. So root over 3 times 2 is going to be 0 point something. So with the 0 point something, it basically means that we will delete this. Sorry. We will delete this and work and continue with the one with infinity. Yes, state 5. This one. We've not we've not yet left it alone. Just watch the pace. Now this one now becomes 0.167. Let's I'm just using random numbers we've not calculated. 0.167. Jesus Christ. Now, okay. um, so 0.167, and this is infinity. So we roll out on this, then assign some value v, also calculate, then compare. So when you compare, let's say ikakuja 9.32. So if you compare 0.167, 9.32, and 11, 11 is bigger. So we roll out on this again. So it forms another state, so on and so forth. Now, how are we going to make a decision? Let's say we formed up a state and we gave them a higher value like v is equals to 25. So this one is going to be back propagated. Here itakuwa 39. Then plus 25 hapa juu will be plus 25. So we are going to take the route that has the highest value of t as you move along. Then that is the so as you can see, this is something that cannot stop. It will go on and go on, and that's why machine learning keeps on improving as you use it. Yeah. Mhm. Highest cumulative value of t's along that route. Mm. Yeah. You've not been regulated just that because of time. We are going to stop there, but you can go and tomorrow. It's something that's not going to stop. By the way, it will never stop. So unless you, as the machine learning engineer, decide that let me stop it at this point, but it will continue going on and on until you get the best result. Given now that one, we can now implement. This is the exactly the Monte Carlo now that we are going to implement for to play with our game. But before we do that, let us play some tic-tac-toe game online. So when I play, the computer takes its turn. When I play, the computer takes its turn. I've been blocked. Then the computer wins. I restart the game. Play, play, play. Mhm. The computer wins again. So this one has actually improved over time. You see how it knows the art, and again it wins. Hey, hey. So why? Wins. So this is the idea that you want to build. The Monte Carlo is going to play it as a computer, and as you see, this is a very complex one, and in media I'm still hard, so impossible will even be impossible. We draw. Okay, now let's build ours. So in this one, we just want to assume the role of a software engineer in a machine learning engineer in a game development company. One thing that you will be asked in your CV, they will ask you no, in the job requirements, OOP. You must know the OOP, object oriented programming classes. Did you realize that this is basically a class? So this is a class, and the class has child nodes. The child inherits from the class. So for you to continue design yetu itakuwa hivi, lazima tukuwe na the following. We must have the following. One of them, we must have the computer player. You must have the human player, which is you. You can name them human move or computer move. So the human move will give X, computer will give O. Then we must have the game itself, and the game here is a tic-tac-toe. So the human move will encapsulate the game, computer will encapsulate the game. Encapsulation has happened. The tic-tac-toe will have different items like X, not spaces, that is inheritance. Then we will have the algorithm itself. These are moves. Here you got to algorithm. So the algorithm is now the Monte Carlo research. So are you ready? Let's build. So first of all, we develop the game, because without the game there is nothing. So we are going to use random moves. Remember when we were looking at the theoretical approach to Monte Carlo research, we looked at the random. We actually assign random value of v's. The same thing is going to happen here. That's why we are doing random. So the computer will just assign a certain random value for itself. Then the copy, to copy basically means the computer can make the same copy of that movie if it so wishes. And again, it can also make a copy of the child node, so that this tree is going to be as like the minimum number of leaves. It will keep on increasing. Then the math is going to just handle the math part of it, like the calculation of the UCBI and everything. So let's define the game. The game will be defined using a class of tic-tac-toe. In the tic-tac-toe, you must initialize board and the current winner. So the board is consisting of 9 spaces. Of course, you must visualize it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 spaces. Then the current winner is none. This current winner will keep on updating as the game increases, and we are going to see how. Then we are now going to print the board. The board is printed using 4 row in the board, and the board contains, remember now this is indexing. Indexing I times 3, then I plus 1 times 3, meaning the row here is I1, I2, I3. So when you talk about that, we must print the board going across. We must print the board going down. Yeah. Then why do we say I plus 1 times 3? If this I, it means it's 1. So the row 1. I plus 1, row 2 times 3 again. I plus 1, row 3 times 3 again. So it keeps on increasing. And this is what we've done with this part here. So I times 3 in Amanisha, that's the first row, all the way up to I plus 1, and it keeps on increasing times 3 for I in the range of 3, 0, 1. Then you just join the rows using the rows. To develop the rows, just join the rows using some vertical bars. It will automatically join them based on this condition that you say you gave up here. Are we together up to that point? Because we are, remember this one, this vertical bar join plus this vertical bar, then join it into this row. That one will form row 1. So how many vertical bars do we have if you print the nini? Say it is 1, 2, 3. So again 1, 2, 3. So this is it. So we're just joining this vertical bar to this, from this to this, and this one forms a row. Yes. Then available moves. In the available moves, how can you make a move? You can only make a move here and here inside the nini, but you can make it diagonally, you can make it horizontally, you can make it another reverse diagonal. So all this we are going to tell the computer. In short, before you build such a game, you must know how to play it. That's even if you're hired in a game developing company, you they want you to develop a new game that you've never played. You will be taken through with the senior engineers. You play the game until you become a pro. That's why in some job descriptions you always see they say this we are a game developing company. Qualification must be game savvy. Uh, experience playing online video games, ABCD. It's just things like that. So they are not just for fun or to lock you out of the job. They are also serving their own interests. Now the available moves we return I for spot. If the I is the move, then the spot is where you make the move. So in Python, if you actually loops iterate through two items at a go, you use the term enumerate, which is going to ensure that these two terms work in sync. So look at that. Enumerate in the self.board if the spot is an empty space. That is when you can make the move. That is only the available space where you can make the move if it's an empty space. Which means that if you delete this, not to be an empty space, then the game will throw an error. If you So you must put an empty space. Empty squares, that's self-explanatory. Just return an empty space in the board. Then make the move. Sasa hapa ninataka uone vizuri sana. You only make the move. And in this case, we have the self, which identifies with the tic-tac-toe game. The square, is an argument that going to form an empty space. Then the letter you are going to use, if you are a computer, you use 0, which you are going to define down there. If you are a human being, you use a letter. You use X. Sorry. So if the board has a square which is actually null, then it is in that null square where you can append a letter. Then there is an inner for loop. It is going to check for the winner, the letter that the winner inputted in that square, or put inside, placed inside that square. Then that's basically the current winner, of which the current winner we are going to look at after playing the game. So, meaning, if I was to build this from scratch without explaining the I codes, I would have just come down here. What we always do, we just come down here and define check winner, then pass. So that after defining, someone who is going to follow the codes before we build it knows that there is a function that is going to check for winner down there. If remember, there are two for nested if statement here. This one is going to check for winner. If the winner has actually placed rightly a letter inside a square, then we return true is the winner. And we only return the winner if the letters are in sync. And the current winner we are going also to see, meaning down there we're going to see the current winner, what happens with the current winner. Uko chini. So let's just continue. It's a long game anyway. Then we return false. This condition will only be done if there is no empty space here. So if self.board is not an empty space, we return false. Otherwise, if it's an empty space, we perform this condition inside it here. Yeah. So let us now check the winner. In tic-tac-toe game, we only get a winner if the following conditions have been met. In tic-tac-toe game, we only get the winner 1, 2, 3, 4. We only get the winner if the following conditions have been met. One, when X or a similar letter goes into this diagonal, or goes into this diagonal, or goes here, or goes here, or here. All this you must code for the computer. So let's see. This is why we are checking the winner. The same thing will apply for, so there is no need for two functions. We're just going to say the current winner and check the letter of that winner. If the letter thinks, there is no problem. So the same thing will happen here. One, heavy, heavy, then heavy, then heavy. So here, it basically means that you must see the positioning. In Python, we start counting from 0. So this one is going to be 0. This is going to be 1. This is going to be 2. This is going to be 3. This is going to be 4, 5, 6, 7, 8. So we are going to say a winner can only be realized if, number 1, the letters are in position 0, 1, 2. The letters are in position 3, 4, 5. The letters are in position 6, 7, 8, or 0, 4, 8, or 2, 4, 6. Hii condition yote lazima ucode. Now let's go. For us to check the winner, we need the square and we need the letter. The square is actually the exact position of that square. So okay, this is just ChatGPT's name. You can name it to whatever you want. But what it's just trying to say is that for you to actually be a winner or a raw winner, you must actually ensure that you fill 3 squares. The square must be divided by 3. And there should be no, that's why we are not dividing, we are flooring. To flow means that there should be no remainder. So we are flowing by 3. So row is equal to dot board. Then the rows that should be filled times 3 again plus 1 times 3. This condition borrows heavily from what we did up here, meaning that if you start, that is just 1 by the way, that if you start in the first row here, if you exhaust it, you can also look through the second row and look through the second row until you finish the tic-tac game. And if all is the same, is actually of the same letter, then return true. That is a winner. Tumelewana. That is for row. The same thing for column. If the columns also are the same way as in the row, then we also return the winner. That is to say, if the same letter is here, like here, that is also a winner. So tumemaliza hizo. Now diagonal. If we divide the square by 2, then you get a remainder. If you floor a square by 2 and you get 0, this is percentage flooring by 2 and you get 0. The remainder, we are checking for the remainder actually. So if anything that you divide by 2 and the remainder is 0, then we look at the diagonal. Then it means that the diagonal 1 is equal to dot board I for I that exists in 0, 4, 8. And look at what we placed here, 0, 4, 8. The same thing, if all of them returns the true letter in the diagonal 1, that's a winner. Same with the diagonal 2, 2, 4, 6. If all of them, that's a winner. Otherwise, if you not get 0, then that's a false. Why are we forcing 0, the remainder to be 0? Because look at this. 0 divided by 0, that is going to throw an error, but technically at the back of your mind, that one is 0. 0, then 4 divided by 2 is 2 remainder 0. 8 divided by 2 is 4 remainder 0. 2 divided by, so we are just forcing this condition that for all the squares where they are positioning, we divide by 2, remainder should be 0, which means we are looking for diagonals in short. So it needs a lot of reasoning to get this without ChatGPT. But even before that, we used to code them. Then ikikuramba, you just go to a Stack Overflow, write your code, then a senior engineer will evaluate it and give you the results after 2 or 3 days. So we've checked the diagonal. If otherwise, if anything that you divided by 2, then it returned something that is different from 0, then that condition is for null and void. Diagonals are not winner. That's only when you can say that someone is a winner. How? When it has filled all the columns, all the rows, and all the diagonals with the 3 letters. Haven't we implemented what we said here? That is, we've checked the winner. Now we clone the game, meaning the game, we assign the game to each and every person. Clone game is a tic-tac-toe game that we defined up there. This is called polymorphism. Polymorphism is a process through which something that was hidden is now being exposed. And is being exposed inside it. This is OOP also. So the clone game dot board is actually the board of the game itself that we define. Then we clone the game. Alafu we write it in the terminal. Is terminal return self.current winner is not none, or if there are no empty squares. You shall build the game. We now build the Monte Carlo research node. In the Monte Carlo research node, this is where the problem is. If you do not get Monte Carlo research how it works, then just forget about playing this game or building this game, you cannot do it. And now this is where your machine learning engineer comes in. And this is where they hired you and not the existing software engineer who was in this company. Otherwise this guy could have developed the TicTacToe. Then wewe ulikuja kwa sababu ya Monte Carlo research. This means that you must get to know all the attributes of the Monte Carlo research. One is the state. Yes. Number two is the parent. Then the children are many. The parent ni moja. That's why unaona self dot parent is equal to parent. Then the children are many. That's why it's a list. And if you can remember very well, the list is an empty list which you are going to fill. We were filling it because, as you can see, back propagation happened. Then we used to come back. We used to come back. So that's why it is empty. But at the end of the game, it will be filled with numerous values. Then sub.move, the move that the children makes is actually the rollout. The number of visits initially is 0, and you are going to always keep on incrementing it. Then the wins, then the number of untried moves. The untried moves are basically the available moves that we define up there that have empty squares. Are we together up to that point? Then once we have the attributes, we can now expand the game. We just what we did there. To move is now self dot untried moves dot pop. Pop in Python removes the last item. So move, here is it. This is the move that we're talking about. Action actually. So uh, someone could, in other courts, you could have found someone saying self dot action is equal to action. But for us we use move. So there is no problem anyway. And bora tu umejua kujua vile utaitumia, there is no problem. Then untried moves dot pop dot pop. But what is the untried moves? The untried moves is set dot available moves. So if you make a move, you remove it from those that are now available. That's why we pop. It was an untried moves. It was initially empty. So when you make a move, you remove it. So it is no longer existing. Then next state is copy dot deep copy self dot state, which means that next state is basically a copy of two. How can I explain this, Jamani, if not showing you? It's just the same thing. It's just that it has different names. So this one and this one are just two copies. The next state, when you make a move, the computer is going to make a move with 0. That's what. Then the child node, the Monte Carlo research node, the next state, parent is equal to self, then the move is equals to move. What has happened here is the back propagation that we were doing. Then the children, several children append child node. You append the value. Actually, I don't know. From here to here is the back propagation. But it starts here. When you are assigning t is equals to some, you see you roll out v is equals to this, that calculates UCB1. When you calculate the child, you append the child node there. Then you turn the child node. That is that one has been expanded. But don't worry, we are still going to revisit this. We have not yet assigned the value of v's and t's because we need to calculate. And that is what we are going to do. This one is just to expand. You see what we did here. This one to build the tree. Now, to get the best child is when we start assigning the values of t's and v's, then calculating. This is why we are going to get the formula now. Best child, C parameter is 1.4. Then the choices weights is child dot wins divided by child dot visits. I mean t divided by n minus 1 plus their constant parameter is 1.4. You can change it to be 2. There is no problem. So that we don't lose, I don't, you don't get lost along the way. Yeah, math dot square root, math dot log self dot visits all over child dot visits. For, Jermaine, is there anything I need to explain there? That's a formula. You see, upper confidence bound formula. Yeah. So it is actually used to find the best child. Then look at what it's doing. It is actually returning choices weight dot index maximum of choices weights. The way you are just choosing the choices weights. Yes, which are the after calculating the upper class bound. Then you simulate that current simulation is equal to copy dot deep copy. So, and I told you if you do not get the meaning of a certain function, you just come and write here copy Python documentation. So returns a shallow copy of objects, returns a deep copy of objects, then the one replaces an object. So a deep copy constructs a new compound object and then recursively inserts copies into it of the objects found in the original. So what we are doing, just what we are doing, uh, if we add t is equals to 0, we back propagate, then that we add there, that's deep copying until we are done with everything. So when you simulate, it's basically to alternate players. Number, we have a letter to be x. If the current simulation, if the current simulation is not uh, fulfilling the value of being in terminal. And what is the value of being in terminal? The value of being in terminal is that the current person is not away, is not like is not available. This is self current winner is not none or is not an empty square, meaning we have a current winner. So we're just saying if there is is no current winner, this one the check terminal is check is terminal is actually confirming we have a winner. Copy here. This one confirms we have a winner. Then the simulation is now saying, anyway, if we do not have a winner, this one negating presence of a winner into bracket, we do not have a winner. So if we do not have a winner, then we can now make the available moves. Current simulation that available moves, and current simulation was to just copy using a letter X. Then move is a random choice. You just make a random choice using the moves. Then the current simulation dot make move using the move and the letter. And the letter is O if the letter is O. If the letter that had done the first move was X, else X. This is basically saying they should do it interchangeably. So they should just do it interchangeably like that. Meaning, if the current letter that has been input, like has been placed in our tic-tac-toe game is X, then the letter that should follow next is O. Otherwise, that's what else. Otherwise, if the current letter is X, like if the current letter that is inside the is O, then the one that should follow the move is X. So this is just an alternating pattern. So we can also say to alternate the moves. If current simulation.current winner is the guy with O, then we return 1, meaning that is the first winner as 1. Else, if the current simulation, the current winner is X, we return -1, the X has 1. Else, we return 0, there is a draw. So backpropagation is actually the number of the set of visits, we add 1, then set wins, we add the result, then the propagate, we get the results back to the negative there is not to minus, but to get the results back to the parent. Keep on filling. Okay, in short, hii kitu hapa ni ile tulikuwa tunajaribu tukinini tunarudi hadi huko juu ku back to the parent. Then we are telling Monte Carlo research that do it in 1,000 iterations, so you can even do it in 1 million, but remember inakula kwa CPU yako, yeah. So do it even in a number of iterations. That is your own. That is a parameter you are going to define. Another value is the root state. The root state is actually the Monte Carlo tree search node. Then the root state there, the root node, Monte Carlo tree search node into bracket root state, and this root state we are going to it's a value that you are going to supply if the current state is either someone playing or not. I This is just a placeholder. It can just be like for I. For I in the number of iterations are 1,000. So we start from 0 to 1,000. The node is equals to root node. Then the current node. While the node with untried moves is empty, and the node is a child, meaning these conditions must be met. If it's just trying to say, if the nodes with untried moves is empty, and the node is a child, then that node is the best child. And again, if the node has untried moves, that's why it is inside the for loop. If it has an untried moves, you can continue expanding it. But don't just expand it, you should simulate, meaning you should fill the values. Then after that, you backpropagate. So this is basically implementing the Monte Carlo research that we were working with up there. Then the root node is now the best child. Then the parameter is 0, and then you make the move. The constant parameter now becomes 0, then you make the move. Meaning we're just trying to get 0 in short, because if the constant is 0, then everything is going to be multiplied by 0. The play is now to just ensure that each and every person play. Game is the tic-tac-toe that we defined up there. Human letter is X, I letter is 0. We just tell them to welcome to the print tic-tac-toe. Then we now game.print the board that the board will define huko juu. While the game has an empty squares, if the game has the current winner, we break. Meaning that we do not make any move. Otherwise, if the game has no current winner, of course, this one is not going to be met at any single point, especially if the game has empty squares. Yeah. So otherwise, let the human make the move. While it is true that the game, has empty squares, that's why unaona iko the same line na hii if, meaning if will never be met. By the way, to be honest, there is no way there will be an empty square and resource a current winner. That's wrong. So if it is true, while it is true that the game has empty squares, then let the human try the move. Then that's why the integer or input should be between 0 and 8. I say that when you make an input to a Python program, it is taken as a text, so you must change it to integer. Then input is to allow you to give something to the terminal. If the move is not in the game of available moves, it's available moves ni ngapi? 0 to 8. So if you make something that is not between 0 to 8, we raise an error. Then we finish the game in Aisha Evo. Except that, and you also tell them that's an invalid move, try again. But if it is true, and this one here is actually okay, then we just make the move using the human letter. Then you print the new board with the your human move. Yes. And if you become the current winner based on all those conditions up there, then you win. Otherwise, if the game is not an empty square, you break. Then AI makes the move now. Computer will think. Then the AI will make the move using Monte Carlo research game. The number of iterations will be 500. Then the game, it will make the move using AI move and the AI letter. Then computer, and what is the AI move? The AI move will actually become immediately after human move. Then the computer will make its move. What if the move must also be between 0 and 8 in the available space? Then we will print the board. Then if the computer wins, we just that. Otherwise, if that is not met, it will become a draw. Then there's this thing here that if the name is actually main, just play the game. This is a standard Python item, which I'm going to give you. Nimesahau, I can't explain what I've forgotten. I'm going to give an assignment to go and do more research. In fact, I know I'm going to meet it in the evaluation here, XAI. So that one I'm very sure. Okay, so that's how Monte Carlo is done. And I was not even interested in up here because when you are added as a machine learning engineer, what you are going to implement is this one. You see this Monte Carlo research node from here. You will work with a senior software engineer side by side so that you can implement all this. Yes, and that marks the end of machine learning day. Not necessarily the end because tomorrow we are deploying. So tomorrow we are going to deploy the PCA and logistic regression. Then after that, you will choose one that you are also going to build and deploy. I highly advise you to go choose from Cargo. Build very well, take your time. You can even choose from YouTube, take your time, build a model, deploy. Then when we meet, it's going to yep. So we stop at that point unless you have any questions. We meet tomorrow.